Good day everyone. Today I will be discussing the theorems on limits. Let's start with the first theorem. Theorem number 1. The limit of c as x approaches a is equal to c. So where c is a constant. So take a look of that. So the limit of our constant as x approaches a, that is any number, that is equal to the constant. Let's have our example. Let's say we have the limit of 3 as x approaches 5, that is equal to, our constant here is 3. Or, let us use the same example. We're just going to change as we approaches to 2 is still, that is equal to the constant, which is 3. Second example. The limit of negative 5 as x approaches to 0. As we are approaching 0, that is still equal to our constant. In this case, that is equal to negative 5. Third, the limit of 10 as x approaches to negative 2. Still, that is equal to the constant, which is 10. So, our first theorem is very easy. Let's proceed to the second one. Now let's have our theorem number 2. For any number a, the limit of x as x approaches a, that is equal to a. So for any number a, we have our x here, that will be equal to our a here. Now to illustrate, let's have this example. Let's say we have the limit of x as x approaches 5, that is equal to our a. In this case, our a here is 5. So, that is equal to 5. Another example, the limit of x as x approaches negative 2, that is equal to our a, negative 2. Third example, the limit of x as x approaches 7, so that is equal to 7. That is our theorem number 2. Now let's have our theorem number 3. The constant multiple rule. Suppose the limit of the function x as x approaches a is equal to L, then we have the limit of the quantity k, where k here is our constant, times the function x as x approaches a is equal to the constant times the value of our limit, which is L. So, if we have our given, we have the constant and the function x, so we can just get the constant multiplying to the limit of our function x. Now to understand, let's have this example. Example number 1, the limit of 4x as x approaches 3. So applying our rule, constant multiple rule, get the constant. In this case, we have the constant, which is 4, times our L, the limit of our f of x, in this case, our x, as x approaches 3. Now, copy 4, we need to get the value of this. Applying our theorem number 2, so this is equal to, our a here is 3, so 3. Now the value of our limit is 4 times 3, that is equal to 12. Another example, let's say we have the limit of 7x as x approaches 1/2. So get the constant, that is 7, times limit of x as x approaches 1/2. So copies the constant times, get the value of this, applying the theorem number 2, that is equal to 1/2. So we have 7 over 2. 7 times 1, that is 7 over 2. That is the value of our limit. Level up to theorem number 4. Now let's have our theorem number 4, the sum or difference rule. So suppose the limit of f of x as x approaches a is equal to L, and the limit of g of x as x approaches a is equal to m. Then we have the limit of the quantity f of x plus g of x as x approaches a is equal to L plus m. Or we have the limit of f of x minus g of x as x approaches a is equal to L minus m. We have the addition or the sum and the difference. Now, to illustrate our theorem number 4, let's have this problem. Number 1, let's say we have a limit of 3x plus 5 as x approaches 1. Okay, we're going to apply our sum or difference rule. So in this case, since we have our plus sign, so we're going to apply our addition. So the limit of f of x plus g of x is equal to, as x approaches a, is equal to L plus m. So number 1, limit of 3x plus 5 as x approaches 1. So according to our rule, this can be written as limit of 3x, this one, as x approaches 1 plus, use the plus sign, limit of 5 as x approaches 1. Okay, we can separate them. We have the limit of 3x as x approaches 1 plus limit 5 as x approaches 1. Separate. Next, apply theorem number 3. So get the constant, that is 3, times limit of x as x approaches 1 plus, in this case, we're going to apply theorem number 1. So our constant here is 5, so the value of this is 5. Okay? Next, we have 3 times. In this case, we're going to apply theorem number 2. Okay, I will write here, use theorem 1. This case, use theorem 2. And this case, theorem 3. Okay. Using theorem number 2, that is equal to our A, because we have the limit x, that is equal to where we are approaching, which is 1. Plus 5. Now 3 times 1, that is 3, plus 5, and 3 plus 5, that is equal to 8. Okay? Next, let us use the difference. Let's say we have limit of 2x minus 6 as x approaches, let's say, what number do you want? A negative? Negative 2 or negative 3. Okay? Applying our theorem, that is equal to the limit of 2x as x approaches negative 3 minus limit of 6 as x approaches negative 3. Now, applying theorem number 3, we have 2 times limit of x as x approaches negative 3 minus, we need to use theorem number 1, that is equal to our constant, which is 6. So 6. Now we have 2 times, use theorem 2, that is negative 3 minus 6. So we have 2 times negative 3, that is negative 6 minus 6, and that is negative 12. That is the theorem number 4. Now let's have our theorem number 5, the product rule. So again, suppose we have the limit of f of x as x approaches a is equal to L, and the limit of g of x as x approaches a is equal to m. Then we have the limit of f of x times g of x as x approaches a is equal to L times m. So to illustrate, let's have this problem. Let's say we have the limit of x times 3x plus 1 as x approaches 2. Okay. Applying our product rule, so product rule, we have our first function multiplying to the second function. So we have that is equal to the limit of x as x approaches 2 times, we have here the limit of 3x plus 1 as x approaches 2. In this case, we're going to apply the previous theorem, just like what we did in theorem number 4. This is RO. Applying property number 2 or theorem number 2, limit of x as x approaches 2, so that is equal to our a, which is 2, so that is simply 2 times, so in this case we need to apply the property number 4, get the constant, that is 3 times the limit of x as x approaches 2 plus we have the limit of 1 as x approaches 2. We need to simplify using the previous theorems. So we have 3. Applying theorem number 2, that it will become our a is 2 plus here limit of 1 as x approaches 2. So theorem number 1, that is equal to the constant 1. Now we have 2 times 3 times 2, that is 6 plus 1. That will give us 2 times 7, and that is 14. Okay, so the limit of x times 3x plus 1 as x approaches 2 is equal to 14. To complete our 4 basic operations, let's have our theorem number 6. Now let's have our theorem number 6, the quotient rule. So suppose we have the limit of f of x as x approaches a is equal to L, and the limit of g of x as x approaches a is equal to m. Then we have the limit of f of x over g of x as x approaches a is equal to L over m, wherein m must not be equal to 0. Now to illustrate, let's have this problem. So let's say we have limit of x over 2 as x approaches 5. Okay. Limit of x over 2 as x approaches 5. So that is equal to, let us apply our quotient rule. We have the limit x as x approaches 5 all over, we have the limit 2 as x approaches 5. Now applying our previous theorems, in our numerator, we're going to apply the theorem number 2. So that is equal to, since we have x here, x approaches to 5, so that is equal to 5 over, in this case, let us apply our theorem number 1. So we have the constant, which is 5 over 2. So limit of x over 2 as x approaches 5 is equal to 5 over 2. Let's have a second example. Limit of x over 2x minus 1 as x approaches to 3. Okay. Now, applying our quotient rule, we can write this as limit of x as x approaches 3 all over limit of 2x minus 1 as x approaches 3. Now, theorem number 2, that is equal to 3 over our denominator, we're going to apply our sum or difference rule. So this is equal to limit of 2x as x approaches 3 minus limit of 1 as x approaches 3. Extend your fraction bar. Next, we have 3 over, simplify, constant multiple rule, copy the constant, so we have 2 times limit of x as x approaches 3 minus, so applying our rule of theorem number 1, we have the constant, which is 1, so that is equal to 1. Now we have 3 over 2 times, apply theorem number 2, so that is equal to 3 minus 1. So we have 3 over 2 times 3, that is 6 minus 1. So we have 3 over 6 minus 1, that is 5. So that is our theorem number 6, the quotient rule. Now let's have our theorem number 7, the power rule. So we have the limit of our function f of x raised to p as x approaches a, that is equal to the limit of f of x as x approaches a raised to our power or the exponent. Now to understand, let's have our examples. Number 1, let's say we have limit of x raised to 3 as x approaches to 2. Applying our power rule, that is equal to the limit of x, in this case we have x, as x approaches to raised to our exponent, which is 3. Now we have limit of x as x approaches to, apply theorem number 2. So this is equal to 2 raised to 3. And that is equal to 2 times 2 times 2, which is equal to 8. Okay. Now let's have our second example. We have, let's say we have limit of x squared minus 2x plus 1 as x approaches to 3. So we have, so first let us apply our sum or difference rule. So that is equal to limit of x squared as x approaches 3 minus limit 2x as x approaches 3 plus limit 1 as x approaches 3. In this case, we're going to apply our power rule. So we have limit x as x approaches 3 raised to, our exponent is 2, minus, we're going to apply our other theorem. So get the constant multiple rule, 2 times the limit of x as x approaches 3 plus, so we have our theorem number 1 applied to this one, that is equal to 1. Now we have limit of x as x approaches 3, that is theorem 2, that is equal to 3, then square, minus 2 times limit of x as x approaches to 3, theorem 2 again, so times 3 plus 1. So 3 squared, that is 9, minus 2 times 3, that is 6 plus 1. So 9 minus 6, that is 3 plus 1, that is equal to 4. So the limit of x squared minus 2x plus 1 as x approaches 3 is equal to 4. And now our theorem number 8. We have the radical or square root or root rule. Now let's have our theorem number 8, the radical or root rule. So if we have the limit of square root of x as x approaches a, that is equal to the square root of the limit of x as x approaches a. Let's say we have our example. Let's say we have limit of x as x approaches 9. Let's say square root of x. Limit of square root of x as x approaches 9. So that is just equal to the square root of limit x as x approaches, we have here 9. Following our theorem number 2, so limit x, that is just equal to where we are approaching, that is 9. So square root of 9, that is, square root of 9 is 3. So that is the theorem number 8.